All right, so in this module, we're going to go through a series of questions that will appear on your quiz as a way of looking at an example of indexing an unknown cubic pattern that we would see in TEM. So I'm going to sort of ask you questions along the way with the ultimate goal that this will help us identify what type of crystal structure this is. And so let's say that I've given you this pattern here, which is also going to appear in the quiz. It's a diffraction pattern, spot pattern. You see the central spot, which is labeled as the origin 000. I've given you labels for two peaks, and this is actually the one that you saw in the previous example. So this spot relates to the set of 220 planes, this to the 200 plane. There's also a scale bar here, which tells you effectively the scale of the image, so that if you blow it up or shrink it, you can use that for more precise calculations. So the first thing I want you to do is, looking at this, and I apologize for the angle it's at, but I wanted to give it as much space as possible. But looking at this spot pattern and the labels that we have, see if you can label as many of the other unlabeled spots that you can. So do as much as you can here, but see if you can label the other spots, thinking about the two spots you have, and if you can sort of fill in the gaps for what the other ones are. So take a stab at that, pause the video, and come back when you've answered that quiz question, and then we'll go through what we've got. All right. So now that you've had a chance to sort of go through and label as many as you can on this diagram, let's go ahead and look at what I've got for you here. So I didn't label every single one, but you can kind of extrapolate to what that is. But let's kind of go through the one that we have here. So I gave you the 220 and the 200. So the first thing to kind of keep in mind is, obviously there's a periodic nature here, as these are periodic patterns for crystal structure. So this is the origin, and then this line here represents the interplanar spacing to 200. And we know that as the HKL values go up, the interplanar spacing goes down. And since we're in reciprocal space, that means the length would increase. And so we know that the distance here is the R value for that. And then if we double that, which is the distance from 000 to this point here, then that is half of the value of 200. And therefore, that should be the 400, because the interplanar spacing should be half. So the fact that it's gotten a longer R value, or greater R value, means that it should be a higher number, because the interplanar spacing is smaller. So we have that general rule. Also, if we look at what a point on the other side would be, so instead of going in this direction, we go the opposite direction, that is effectively the negative direction. And so this is equal distance here as it is here. And so this should be bar 200 in that case. And then this would be bar 400, because again, the same rule would apply. So that's how we're getting basically these labels right here. All right, so the next thing we can kind of look at is, so effectively this direction is the x direction, right? Because we're talking about 200 and 400. And so we can also look at what a peak over here would be based on the value here. So since this is 220, that means it's going in both the x and y directions. And so that means that this must be the y because this is the x. And so this is an equal distance, and it should be in cubic. So this is the 0 to 0. And then this would be the negative that. This is the 0, 4, 0, and et cetera. So you can label those in this line. So we're basically looking at the xy plane effectively in this case. And this is 2, 2, 0. So if we go and double the distance, that would be 4, 4, 0. And then we can look at bar 2, bar 2, 0 in the same way, and then bar 4, 0 down here in the corner that it's being hidden right now, right here. So same thing there. And we can also look at getting the values here and here in a similar fashion. And you can keep kind of going on. I stopped at some point, but that kind of shows you. So basically, from symmetry of the crystal, that's how you should be able to sort of fill in the blanks of these patterns. So that's where I'm getting this information. That's how I'm filling this information in. All right, so let's look at the next part of this. So I mentioned that, again, we're only looking at a subset of the diffracting spots because in our experiment, in our TEM, the beam is parallel to the zone axis. And so we need to determine the zone axis, and that will tell us the orientation of this crystal. So looking at the peaks you have, see if you can determine the zone axis. Pause the video, go answer that question in the quiz, and then come back and I'll see if we can kind of go through and see if you can understand the zone axis part of this. All right, so let's look at how we get this part. All right, so it's so I'm going to go ahead and say that the zone axis is the 0, 0, 1. So let's see if we can determine how that's the case. So the first thing you'll notice is you're looking at all these points here. There's no z, right? They're all zeros in those cases. So that's kind of one hint here. And then if you look at all these HKL values, if you apply the Weiss zone law and all these kind of observable HKL values, you'll see that the 0, 0, 1 fits that expression. So again, if you're unclear about that, go back and look at the Weiss zone law, and using these as the HKL values, you should be able to get that it's 0, 0, 1 for the UVW, or the zone axis that all of these planes are a member of. And so that's important because basically in this crystal, what that's telling us is that the TEM beam is parallel to this 0, 0, 1 direction. So basically what this is saying, and this is pretty powerful, because in our orientation that this diffraction pattern was taken, the electron beam in the TEM is parallel to the 0, 0, 1 direction, so parallel to the z-axis. And in that case, we will get this pattern. If it was parallel to the 1, 1, 0 or the 1, 1, 1 directions, we would expect different spot patterns for the same exact crystal structure. So not only from the diffraction pattern can we potentially get what the crystal structure is, but we can also get orientation. And so that's powerful, right? Because if you're looking at a TEM sample, it is often useful to know what the orientation of that crystal is. And from this, that's what it's giving us. And so that's powerful for things like polycrystals, where we can determine what the relative orientations of the different crystals. All right, so let's go to the next question here. So I've given you a table from Cullity that we've used before, basically the values of S here. So based on this table that I've clipped here in the slide for you, see if you can determine, based on our pattern and everything we've done up to this point, so make sure you do it in order, but based on all that, see if you can eliminate any of these cubic structures based on the information that we've obtained so far. So I'm not asking for a particular answer yet, but just which ones can we eliminate based on information about these various structures. So answer that, pause the video, and then come back and we'll see if we get the same answer. All right, so let's see which ones you come up with and what crystal cubic structures you think that we can eliminate. So compare your answers to what we're getting here. So we're going to kind of go through and look at some of the various systems. So let's start with simple cubic. So in that pattern, you'll notice that the first peak or a spot that we have is the 2, 0, 0. So let's go back real quick and look at that, right? So this is the first peak that we see. There's nothing, you know, if it was a 1, 0, 0, or yeah, the 1, 0, 0, you'd expect it somewhere here, right? Again, because of the same rule with the geometry of the crystal. But we don't see that 1, 0, 0. So in effect, that means that since there is no 1, 0, 0 spot, and we would expect to see it with this zone axis, then this tells us that it's not simple cubic because there isn't that 1, 0, 0. So from process of elimination of what peaks aren't there, we can get that it's not simple cubic. All right, so next, let's go through diamond cubic. If we go back to this table here, you don't expect to see the 2, 0, 0 in diamond, right? And so that means that we can eliminate diamond because our pattern has 2, 0, 0, and that wouldn't show up in a diamond cubic pattern. So we can eliminate diamond cubic because of what we do see in our pattern. All right, let's go back. And I apologize if you can hear my cat in the background, but let's go ahead and go to the next one. Let's look at body-centered cubic. Here's so in our pattern, we see the 2, 2, 0, but again, we don't see the 1, 1, 0, which from geometry we'd expect somewhere right here, right? And so whereas, you know, again, we expect to see the 1, 1, 0 for body-centered. So from the lack of the 1, 1, 1 spot, we can exclude body-centered cubic because our pattern doesn't have the 1, 1, 0. And again, that's something that you can compare to the zone axis we have, and you should expect to see this. So you also have to compare it to which patterns you would expect to see based on our zone axis. So basically, so far, we've been able to eliminate simple, diamond, and body-centered. So this one, and this one, right? So basically, by process of elimination, we should be able to determine if it's cubic, then it's going to be face-centered cubic. And these, again, these are the peaks we'd expect to see, and then we can eliminate those that don't match with the zone axis that we have. All right, so that's what we have so far. And so again, we already talked about the fact that only leaves us with face-centered cubic. So we basically know what it is right now. We know the structure. We've got this pattern here. I'm going to give you the camera angle, but you can the camera angle there. You've also got the scale bar there. And so now, using this information and the equations and the previous sections, see if you can calculate the lattice parameter from this pattern. And then, again, pause the video, come back, and we'll compare what you've got to what I've got. So see if you can calculate lattice parameter from this information so far, and we'll come back and see if we get the same answer. All right, so now that you've had a chance to work on the lattice parameter here, let's see what we've got. So again, you're going to need to use that expression that we had that combines the R values with the lattice parameter because we basically know the R values from the diffraction pattern. We're given the camera constant, which is in essence both of these. So the lambda times the camera length is the camera constant. And then we know the HKLs because we've indexed and we've gone through that math. And so we can rearrange and solve for the lattice parameter. And we get this expression. So just a rearrangement. And so then we're going to plug in the camera constant. So again, from the units, it looks like an odd units, but keep in mind that this, in essence, the camera constant is your kind of conversion between what you're seeing on your screen and what it is in reciprocal space. So that's why we kind of have the interesting units here. So 50 angstrom millimeter. And we know for the given one that we're using, and you may use different points depending on which one you choose. For this one, I use the 2, 0, 0. So that would be 2 squared, 0 squared, 0 squared. So we get that. And then because I used one of those, either the 0, 2, 0 or this 2, 0, 0, we see that distance between those two points, and so that's the same as these 2 points, is going to be 17.76 millimeters. So you don't even really have to calculate anything. If you want to use a different one, you might have to do some calculation there. And so if we plug all that in, that information, we get 5.63 angstrom. So that's our lattice parameter. If you chose to do something different, then here's my math for the 220 peak as well. And again, you can get other ones, but it'll just be different variations, but you should be able to get the same lattice parameter. All right, so a couple last things I want to do here is let's go ahead and calculate the angle between the 200 and the 220 planes. So calculate that and then compare it to what we see in the pattern here. So pause it, see if you can calculate that value real quick, or look it up in the table, and then we'll compare that here. All right, so let's compare what you've got angle-wise to what I've got here. So I did it both ways. I've got the angle equation and I've got the table. So here's the angle equation with the two planes. And so if I plug in all those values, basically rearranging for alpha, so we get the cosine inverse and then the expression of those two planes. Basically all of that, you end up getting 45 degrees. So make sure you're looking at degrees versus radians if you're comparing. And then if you want to compare 200 to 220 from the plane, this version here, so I've got a 100 type and I got a 110 type, because again, remember the angle won't matter if it's 220 versus 200 and 100 and 110. So the angle will be the same. So 45 from both. And if we go back to the pattern, that looks like a 45 degree angle because this is a 90 and it's halfway in between. All right, so keep in mind, again, if the pattern was, the structure was unknown, instead of doing kind of what we did, what we would instead do is we would compare the ratio of R values. That's something we didn't do in this example because we were able to determine that it was FCC already. But we were able to compare the ratio, we could compare the ratio of these R values and compare them to specific structures in order to obtain it. Kind of like we did in the manual indexing method for cubic, but using ratios instead of the specifics here.